Hello and welcome to Empowered Learning. The purpose of this video is to discuss a concept in calculus called differentials and to see an application of that particular concept used in what we call linearization of a function. So first, we're going to spend some time talking about differentials because we're going to need to know that concept to be able to eventually get to linearization. Before we get started, one major thing that I want to just kind of put into your mind as we start this study here is that our end goal, of course, is to study linearization. And so all we're really trying to do is figure out a fancy way to express the point slope version of an equation of a line in calculus terms. And we're going to use a combination of derivatives as well as these things called differentials and incrementals to be able to do that. So all that we are going to be talking about here is going to be moving towards that goal post to eventually say, hey, if I want to estimate what a function may act like for a small interval of x values, I can approximate it to look like this line, and we're going to use the point slope version of an equation of a line to do that. And just as a quick review, the point slope version of an equation of a line just looks like this. So if you remember, y minus y1 is equal to slope times x minus x1. So we're going to rewrite this in a fancy way so that we essentially just solve for y. Okay, that's really the main goal. All right, so let's get started here. So first, I want you to recall that if we have some function y, which is going to be a function of x, then we define the derivative in terms of the definition of the derivative as limit of the difference quotient. And so what you see here is me expressing the limit of the difference quotient in 4 different ways, okay? Now I'm doing this because you've probably seen this form first, probably seen this form second, and of course these two alternative ones, you may or may not have seen those as much, but all 4 of these are the same thing. If you remember, the slope of a line is just basically y2 minus y1 over x2 minus x1, where these x and y values here refer to points, x1, y1, and x2, y2 that are on a line, okay? So we name this point A, name this point B, and we have this here. Then, of course, the change in y values over the change in x values. Of course, we would call this delta y over delta x. That's another way to say it. So the change in y values over the change in x values would just be the slope of that line, okay? And we normally refer to this as the slope of a secant line if we're dealing with some function to where, and I'll kind of draw something in here to kind of make my point. So let's say we have a function that kind of acts like this, where it's doing like that and it curves up and it goes like this. So when we have a line intersect a curve at exactly 2 points, then we call it a secant line, okay? So all this is background information for what I'm trying to talk about here. The main thing I want you to get out of what I've said thus far is that we have different ways of expressing the derivative as a limit of the difference quotient. And of course, the difference quotient, which is just a fancy way to describe the slope of a line, can take on many different forms. Our goal here is to work more so on this form to see how that's going to eventually create what we call a differential, so that we can rewrite the way that we express derivatives in what we call differential notation. And then, of course, we'll talk about conceptually what that means, okay? So we have all 4 forms of the definition of a derivative in terms of limit of the difference quotient. And so down here, what I am doing is basically saying, hey, the other 3 forms, how does all this relate to this last form here that I've circled, okay? So we see here that the change in y, or delta y, is going to be the change in, or the difference in between y2 and y1, which is the same as the difference in between f of x2 minus f of x1. And of course, y2 here is just a result whenever I plug in x sub 2 into my function. And of course, y1 is the result whenever I plug in x sub 1 into my function. Here, if I was expressing my points not as x sub 1, y sub 1, and x sub 2, y sub 2, if I was expressing it as x, f of x as the first point, and x plus h, f of x plus h, as the second point, and to be clear here, this would be my x1, y1, this would be my x2, y2. If I was to substitute all this into the equation of a line, equation of slope of a line, then what I would eventually have is what you're seeing here, okay? And of course, the f of x plus h minus f of x is just going to be the numerator of that, and that's why it's just the change in y, okay? And of course, lastly, if I was to take the same points now and express it as a f of a, and then the other point as x, f of x, then again, I could rename this as x1, y1, x2, y2, and I get this form of the difference quotient, okay? And again, what you're seeing here is just the numerator for that. So you see that this delta y, we can express it in many different forms. To make life easy for us, we're going to keep it in this form for now, in doing our derivation for this thing called a differential. So just like how I've showed you how all this is really tied to the slope of a line in that particular formula, we can kind of do the same thing with the delta x, just a change in x values. And depending upon what form of the difference quotient you're looking at, the change in x values looks different, okay? Of course, change in x values here. If it's a difference in between two actual values that you know, it's here. In this form of the points, of course, this is one x value, that's the other. And of course, here, this h that you see here is actually, I'm going to do a different color here, move it over. It is actually the difference in between x plus h and x, okay? So that's what this actually is, because again, the difference in between this and this is just going to be h. All right, so now that we kind of see how all these forms of the difference quotient are connected to the delta y and the delta x, now we want to talk about what the delta x and delta y actually mean, okay? So with the delta y, we also interpret this as a vertical distance, or of course the rise of the slope of the secant line. So that's what I was trying to show you here, okay? Now, the point that I want to make here is that what this delta y actually is the actual change in the y values going from one x value to another. That's what it actually is, okay? And of course, delta x is just going to be the change in the x values, okay? So you can think of this as the rise. You can think of that as the run, okay? None of that has changed from when you learn this in algebra. What we're doing now is, now that we are expressing things in terms of, in this delta notation, then I could rewrite this first form of the difference quotient that I had here with the f of x plus h minus f of x, all that divided by h. And here, I could replace my h's with delta x's, okay? And you see that I've done that here, okay? And I could also express everything this way. where again, if you remember, we had limit as h approaches 0 up here. So you see where we had limit as h approaches 0, but we can change that h to a delta x. And so what we could do is really express our derivative or limit of difference quotient in terms of this delta notation, okay? And so this is kind of where we're trying to go with this so that we can eventually get into this differential form, okay? So all that was just to basically set up, hey, we're about to make a transition here and interpret this as a derivative and kind of move forward into the actual notation. Now, we call the limit, and I'm going to back up here, we call this limit here our way of expressing the derivative in terms of incrementals, okay? Now, again, remember that what this delta y here just means, it is just the actual change in y values. That's all it really is. But we give it this fancy name of an incremental, okay? And so, of course, since we're changing y values, it would be a vertical incremental, whereas delta x is going to be change in x values. So that will be a horizontal incremental, okay? Now, if we consider the difference quotient in incremental form, which is what we have here, where this delta x is really small, but not quite 0. So let's say we're estimating that the change in x values is going to be about 2/100ths of a unit or whatnot. Or we could actually make this negative if we're going to, let's say, from like 6 to 5.5 or something like that. In this case, let's say from 6 to 5.9, there's a change of minus 0.1. Then if we look at these incrementals here as these small changes, then the expression here is what we call a good approximation of the derivative, okay? And we're saying approximation because we know that for the derivative, the definition of a derivative, well, one of the interpretations of it, I should say, is instantaneous rate of change. So meaning if I want to find how fast something is changing at an instant or a snapshot in time, that is what the derivative is, okay? And of course, we know what that really is just limit of the difference quotient, and the difference quotient is really just this. So when we use this expression of dy over dx to represent the derivative, what you're saying here is that you want dy delta y over delta x to equal this, but you're saying delta y is as small as possible. So it's approaching 0 and it's as small as possible, okay? Same deal here. This is approaching 0. So the difference in between the two y values and the two x values theoretically is going to be 0 here. But of course, we can't say 0 over 0 because that's an undefined case. And in terms of limits, it's an indeterminate case, okay? So the point here is that we could use the actual instantaneous rate of change as a means of being able to estimate approximate rate of change, okay? And so that's the big idea here, okay? So moving forward, if we say, hey, I can approximate actual instantaneous rate of change with approximate rate of change, if I just multiply both sides by delta x, then what this tells me is that I have a way of estimating the actual change in y values going from one x value to another by essentially using the derivative of that function, if I know it, times the actual change in the x values, okay? So I'll say that again. I can actually estimate the actual change in y values, that's what delta y means, by using the derivative of my function times the actual change in the x values. So to give you a quick example of that, let's say that my x sub 1 is 4, and my x sub 2 is 4.2, okay? So that means that my delta x, which is the difference in between x sub 2 and x sub 1, is just going to be the difference in between 4.2 and 4, which is 0.2, okay? So if I wanted to figure out, well, for some function y is equal to f of x, what is going to be the change in the actual y values? What I would do is this. I would say that the actual change in those y values would be the derivative of that function evaluated at 4, because that's where I started from. And I'm going to multiply that times delta x, but I know delta x is 0.2, okay? And so all I'm doing here is I'm using the slope of the tangent line, and I'm multiplying it times the change in the x values to figure out the change in the y values. Now, before we move forward here, remember, delta y is just the change in y values here. And remember that the derivative of a function at a particular x value is really just the slope of the tangent line of that function at that particular x value. And remember, delta x here is just the change in x values. So when you see this, notice how this looks like the point slope version of an equation of a line, okay? And so this is what I was saying at the beginning of this video, that when we talk about all these differentials, incrementals, and eventually get into linearization, which is going to be an application of this, all we're really doing is coming up with a fancy way to express the point slope version of an equation of a line and using it to approximate how some function y is going to act, okay? All right, so let's move forward here. So again, the expression that we have been talking about here, the derivative of a function of x times delta x, has an important theoretical and practical applications for it. And what this actually ends up being is a differential, okay? So the whole concept of a differential is this derivative of a function of x times delta x, okay? And the purpose of the differential is to help you approximate the actual change in y values going from one x value to another, okay? So here we see that the differential here is going to be, you just call it dy here, is equal to derivative of a function of x times delta x, okay? Of course, if you just call your function f, then you can look at it this way. And again, all this comes from the fact that the actual instantaneous rate of change is going to be approximated by the slope of a line, basically, okay? Now, again, delta y represents the actual change in y values, okay? This differential here represents the estimated change in the y values, okay? And the reason why it is an estimate here is because this value is going to be finite, okay? Meaning that it's going to be a value that is going to be significantly larger than 0, okay? Now, in theory, when we say dx like this, whenever we have dy over dx, and we talk about this dx part, what this really is a delta x as x approaches 0. So another way of saying it is, if I can think of the smallest possible theoretical change, and so that's what I have down here, it is interpreted as the smallest possible theoretical change in the x values that is greater than 0. That is essentially what the dx here is when we use it in this Leibniz notation for a derivative. When we replace dx with delta x, what we're saying now is that we're looking at a change that is not the smallest theoretical change. And because it's not the smallest theoretical change, our exact calculation now becomes an estimate, okay? And so that's why when we say the differential of y is going to represent an estimated change in the y values, that's why we say that. Okay. All right. Now, application of what we're talking about here is linearization. Okay. Now, the basic idea behind linearization is this, and I'm going to focus on this graph here for a second before I get into all the math notation. So if you notice for this function f of x here, we have this function, we've identified this point a f of a. And you see that we actually have a tangent line going through that particular function at that point, a f of a. Okay. And remember that the slope of the tangent line represents the derivative of our function at this particular x value. And of course, this x value here is just a. If you notice right around here, if we look at our line and if we look at our actual function f of x, they are really, really close to each other. Okay. So if I needed to do an estimate of how my function f of x is acting close around when x is equal to a, then one way that I could do that is I could just say, well, hey, if I knew what the equation of the tangent line was, I could just use that to make my approximation. Okay. And so in this small little area that I've circled here, what we are essentially saying, and of course it's not exact, but what we're essentially saying is that my function, f of x, is acting a lot like this line y equals L of x. And so if I want to give a quick estimate of what f of x is doing around x equals a, or real close to it, as far as, let's say if I wanted to change, let's say if I wanted to go from x equals a to x equals a plus h, and this was a small incremental change here, I could actually use my equation of the tangent line to be able to make that estimation. Okay, so that is essentially what linearization is. My function and the tangent line for that function at a particular point are really, really close to each other. So both of those functions act very close to being the same thing around a small interval of x values. Okay. So this is why I say linearization is used to estimate changes in the y value for a function, given that we know the change in the corresponding x values. So we know we made this change. I'm trying to figure out what this change in y values is here because of that. And I don't have to be exact. I just want to estimate. Okay. Now, how do we actually put together this linearization function? Or put another way, how do I come up with the equation of the tangent line? That's essentially what I'm doing. Find the equation of the tangent line as it goes through this particular point. Well, here we recall that we can use our derivative to estimate the instantaneous rate of change of our function here, which means that if we have it in this form, we can estimate the change in y values by using this differential here. Okay. And like I explained to you before, the delta y is just a change in y values. The delta x is just a change in x values. And the derivative of this function at a particular x value, mainly at x equals a here, but I'm just calling it x of 1, that is going to be the slope of the tangent line. Okay. And so, again, you see how this looks a lot like the point slope version of an equation of a line. So if we rename some things here, and here I say let y sub 2 just be y, let x of 2 just be x, let x of 1 be a, and let f prime of x of 1 be f prime of a. I think I got them all covered here. Then, oh, yeah, I forgot one. There should be y1. Yeah, so y1 should just be f of a. I thought I stated that somewhere, but I didn't. So this is f of a here. So if we replace all of this, then of course you see that we end up having this equation here. And if I add f of a to both sides, I end up having this. Okay. And what this equation tells us is that we can estimate a new y value for some function f of x if we start at some point a f of a, hence why you have a in here, and of course f of a there, and move horizontally a distance of x minus a. And remember, this is what our delta x was here. So note that if x minus a is positive, then you're moving horizontally to the right, and if x minus a is negative, you're moving horizontally to the left. So we can have both positive and negative answers for this situation. So that's the reason why I'm stating that. All right. So the last thing is that if we take this approximation sign and actually make it an equal sign, okay, and we let y sub 2 be L of x, then what we essentially have is our formula for what we call the linearization of a function f of x at x equals a. Okay, so this formula here, you see where it comes from now. Okay, we basically just took the concept of a derivative and the concept of the slope of a line, kind of merged those two together, put in the interpretation of slope of a tangent line going through a point of a function, rename some things, and we essentially have what we call the linearization of a function. And what the purpose of this particular function here is to do is to tell you, hey, I'm going to tell you what your new y value would approximately be based upon knowing the slope of the tangent line going through my function at some specific point a f of a. Okay, and of course the idea here is that you only want to plug in values of x here that are going to be really, really close to a. Okay, and it really depends upon how the function acts, or put another way, it depends upon for how long does the slope, or for how long does the equation of the tangent line hug the actual function really, really close. Okay, for functions where that happens longer, the interval of x values that you can plug in for where this particular estimation would be, pretty accurate, is going to be longer. But of course, if those two functions kind of diverge from each other relatively quickly, then that interval is going to be much shorter. Okay. All right. And so because of that, we're basically saying in that in that tight interval of x values to where both this line and our function act pretty much the same, we're saying that they're going to be approximately equal to each other. Okay. And when it comes to linearization, I mean, that's pretty much it. So what we want to do now is get into some examples so that we can see how this is actually used. So for our first example here, we're just going to take our function f of x that we're given, and we want to figure out what is going to be the linearization of it. And of course, for this, we're going to do it at when x is equal to 1. So that indirectly is going to tell us the point on the graph where we want to essentially come up with the equation of the tangent line. Okay. So again, this linearization here, what this essentially is the equation of the tangent line. That's pretty much all it is. We're just finding the equation of the tangent line at the point 1 f of 1. So here we know that since a is going to be 1 in this case, then we need to find out what f of 1 is. So we just plug in 1 everywhere where we see x. We see that we get 41. When we take the derivative of this particular function, we see that we get 24x minus 3x squared. And then when we evaluate the derivative of this particular function at 1, we see we get 21. And of course, our interpretation of derivative of a function at a particular x value is slope of the tangent line, okay? And so what we're seeing here, just to kind of draw out what this may look like, this function could possibly look something like this. And what we are assuming here, based upon the information that I'm getting, we have a point 1, f of 1, and I'm going to try to draw this. So let's say here, let's say at this point here, we have the point 1, f of 1, which is 41. And what we have is this line here. It's going to go through that point. And this line is what L of x is going to be. Okay. And here, for this area here, for that portion of the graph of our function f of x and our tangent line L of x, we see that these two functions are relatively close to each other, so the y values are relatively similar. So we're going to say that, hey, our function here acts a lot like this line L of x for x values that are within this red circle that I have here. Okay, and so conceptually, that is what it is. That is what we are doing. Okay. All right, and of course, this is my function f of x here. All right, so once we find all this information here, we find out what essentially f prime of 1 is. Of course, put a 1 here, and we put a 1 there. Then we put everything in, and we see that this ends up being our equation of the tangent line, which we're calling the linearization of our function f of x. And if you want, of course, you can, go ahead and simplify this and say this is 41 plus 21x minus 21, and just say that this is 21x plus 20. And you can do that if you like. All right, so let's look at our next example. So again, we want to do the linearization of this particular function. So the linearization is going to be L of x. It's going to be f of a plus f prime of a times x minus a. Okay. And again, our a here is going to be 1. So that means we have to find out what f of 1 is. We have to find out what f prime of x is, so that we can find out what f prime of 1 is. So we plug this in. Of course, this will just be 590 here. The derivative of this function would actually be the derivative of 590 times x raised to the negative 1/2. And that will be 590 divided by negative 2 times x raised to the 1/2 minus 1. And I'm just going to write 1 as 2 over 2. And so now from there, we will say that, yeah, this is going to be negative 295. This is x raised to the negative 3 over 2. And this will be 295. I'm just simplifying this to make it easier to evaluate once I actually have to plug something into it. So this would be square root of x cubed, which this is actually going to be absolute value of x times square root of x. And of course, that comes from the fact that this is just square root of x squared times square root of x. And by definition, square root of x squared here is absolute value of x. Okay. All right, so now that I have that, then of course f prime of 1, all I have to do now is just stick in 1. And this is absolute value of 1 times square root of 1. Of course, that just ends up being a negative 295. So I have f of 1, I have f prime of 1. So I think we pretty much got everything that we need. So therefore, the linearization of this is going to be, I'll just write this in, f of 1 plus f prime of 1 times x minus 1. And we know that f of 1 is 590. F prime of 1 is going to be a minus 295. So, and we have x minus 1 here. And so you can leave it in this form, or you can keep on writing this and get it into basically slope-intercept form, y equals mx plus b. So if we do that, we'll have 590, 295x minus 295. And of course from here, 590 minus 295, that will of course be 295. 295. And so this would be the linearization of this particular function. All right, so for our next example, we want to do the linearization of cotangent of x, and we want to do it for values of x, for the value of x of pi over 4. So basically, we're trying to come up with a line that's going to approximate the behavior of cotangent of x around x equals pi over 4. Okay, so again, we know that this is the formula for the linearization, and we're going to let a in this formula be pi over 4. So of course, we got to figure out what f of pi over 4 is and f prime of pi over 4. So of course, we just plug in pi over 4 into cotangent, figure out what it is. And since cotangent is the reciprocal of tangent, we know that this is going to eventually just be 1, because 1 divided by tangent of pi over 4, tangent of pi over 4 itself is just 1. So 1 divided by itself is 1. We know that the derivative of cotangent is going to be negative cosecant squared. And by the way, if you don't remember that, you can always derive it. If you remember, cotangent is the same as just cosine divided by sine. So just letting c equal cosine and s being sine, if you take the derivative of that by using the quotient rule, quotient rule says low function times derivative of high. So low function times derivative of high function minus high function times derivative of low function, and all that over the low function squared. Here, this s times s here is kind of like saying a minus sine squared, and cosine times cosine is a minus cosine squared. And this is sine squared here. And notice here that sine squared plus cosine squared is 1. So that means minus sine squared minus cosine squared is going to be minus 1. And of course, the reciprocal of sine is cosecant. So that means the reciprocal of sine squared is going to be cosecant squared. So that's how we get that. All right. So after that, we just take pi over 4, plug it into our derivative. And of course, remember that cosecant squared of pi over 4 is just 1 over sine pi over 4 quantity squared. And from here, we know that sine of pi over 4 is just going to be 1 over square root of 2. And if we square that, it's going to be 1/2. And of course, that ends up being a negative 2 here. So now we have everything that we need. So now it's just a matter of plugging in everything. So we know that f of pi over 4 is just 1. We know that f prime of pi over 4 is going to be a negative 2. And that's what we have here. And then we just rearrange it. Okay. And so we see here that L of x just ends up being a minus 2x plus, and of course, this is an irrational number, but it's still just a number. So this still is looking like it is in y equals mx plus b form. Okay. All right, let's move on to the next example. So for our next example here, we want to find a linearization, basically a line, equation of a line that's going to estimate what f of x is going to be at a suitably chosen integer value, which we're calling b here, at which the given function and its derivative are easy to evaluate. So the hint here is we want to pick a number that's an integer that's closest to this value that's given to us here. Okay. So the closest number that's an integer to 8.1 is just going to be 8. So we're going to say let a equal 8. Then that means that the linearization for this particular function around a equals 8 is going to be f of 8 plus f prime of 8 times x minus 8. And so this tells us that we need to find what f of 8 is and what f prime of 8 is. So f of 8 is just going to be the cube root of 8, because this is what f of x is, and that is simply 2. If I take the derivative of this particular function, then this is like me taking the derivative of x raised to the 1/3, which is going to be 1/3 x raised to the minus 2/3. And here I'm just going to rewrite this. This will be, so this is another way to rewrite it, because it'll be easier for me to evaluate it in this form. So now that we have that, this means that f prime of 8 is just going to be 1/3 times the cube root of 8 squared. Okay. Or simply put, I'm going to rewrite it this way. Cube root of 8 times cube root of 8. I could rewrite it that way. And so now, of course, we know the cube root of 8 is just 2. So that's 3 times 2 times 2. And that ends up being 1/12. So now that we know what f of 8 is and f prime of 8 is, then we just need to substitute everything in and then try to simplify it to get it into slope-intercept form. So f of 8, that's just going to be 2. F prime of 8 is going to be 1/12. And then, of course, we have x minus 8 here. And so this is going to be 2 plus x divided by 12 minus 8/12. Of course, that'll be x divided by 12. And here we know that 8 divided by 12, both of these have a common factor of 4. So 4 goes into 8 2 times, 4 goes into 12 3 times. And so we just have here 2 minus 2/3. And we could rewrite 2 as 6 divided by 3. And so now this means that our final answer here just ends up being x divided by 12 plus 4/3. And that would be the line that approximates what cube root of x would act like near x equals 8. Okay, so in this next example, what we are going to do is actually see what we mean when we say that the actual change in y values, which we represent by the change in y or the vertical increment y, we can estimate this actual change by doing what's called the differential of y. Okay, so this example will actually show you that. Now, we have already dealt with this particular function before. So we've dealt with this, but we're going to do it at a different x value here. And we're going to calculate what the differential of y is at that x value, as well as what the vertical increment or the actual change in y values will be. And we are assuming that delta x here is going to be 0.1. So put that another way, remember that delta x here is going to be x2 minus x1. So if x of 1 is going to be 2, and we horizontally move to the right 1 unit, then that means x of 2 is going to be 2.1. So that's essentially what that's trying to tell us here. So of course, I've actually kind of done this here already. X equal to 2 and delta x equal to 0.1, then x of 1 is 2, then that means that x of 2 has to be 2.1. So now we just use our different formulas to see what this actual change in the y values is going to be versus the estimate. Okay. So first, what we are doing here is we are doing the estimate. And we're doing the estimate because we are using the differential. So the differential of y is just going to be the derivative of our function evaluated at 2. And we're going to replace this with delta x. Okay. So here, if we do this, remember that although I'm writing the dx there, we're actually going to replace it with the delta x. And so now you see that I've actually introduced that. So wherever you see x, you're going to put a 2. And of course, here, the derivative of our function, we found that already. And that's what this is. Because remember, this is the original function. Derivative of a constant is 0. Derivative of 12x squared is 24x. Derivative of x cubed is 3x squared. So that's how we get that. And we just plug in 2's everywhere, and our delta x is going to be 0.1. We do all that, we see that we get a value of 3.6. And so what that tells us here is that the estimated change in y values from x equals 2 to x equals 2.1 is going to be approximately 3.6. Okay. Now, if we wanted to know the actual change, then of course, what we would do is just take the change in the y values based upon those x values. So I essentially find what f of 2 is, and then I find what f of 2.1 is, and I take the difference. Okay. So as you can see here, f of 2, that ends up being 70, and f of 2.1 is going to be 73.659. And when we actually do the difference of those two values, notice that we're kind of close. Okay. So the estimate here was 3.6. The actual is 3.659. Okay. And so now you see why we say that the differential approximates the actual change in y values, or the differential approximates the vertical incremental in this case. All right, let's move on to the next example. So in this next set of examples here, what we're trying to do is get practice rewriting derivatives written in differential form. Okay, or in other words, using derivatives to come up with a differential form for a function. And so we need the skill of writing derivatives of some function in differential form so that we can use those formulas in modeling. Okay, so we're going to have some word problems that comes up later on in this video, to where we're actually going to have to rewrite or use the differential form to be able to model the situation that we're talking about. Okay. And so, for example, if we're going to model how much a diameter of a tree is by f of t, then the differential that is expressed by this particular equation here, that'll be a formula to help us change, help us to estimate the change in the diameter of the tree, given that we know the change in time, or we know the change in some other parameter like the diameter or radius or whatever. Okay, so basically we'll be studying the change in something by knowing the change in something else. That's the main point that I'm trying to get across, and differentials help us to be able to do that. And essentially what we're doing when we use these differentials is we're doing what's called sensitivity analysis. Okay, and so what that means is if I make a small change over here, how does that affect this result? Okay, and of course, a small change leading to a big change is going to be, something that's significant, versus if I make a small change over here and I end up with a small change over there, it's probably really not going to make a big deal. Okay, and so it's good for us to know in some applications, especially business applications, when that happens. All right, so let's look at these two examples here. Since I have B already worked out, we'll look at that first, and then we'll do example A. Essentially, all we need to do is figure out what dy is, or the differential of y is. Okay, so for these problems, we essentially just figure out what the derivative is. Say the derivative is equal to dy over dx. So we know that the derivative of a function is dy over dx. Once we find out what the derivative is, we just multiply both sides of our equation by dx. Okay, so not anything real sexy to this. It's just a matter of getting it done. So for this function, of course, I've elected to change this cube root of x squared to put it in fractional exponent form so that I can distribute it across both terms here. So I can just use the differentiation rule, the power rule, to be able to do that. And of course, now just take the derivative of both of these terms. You see, once I do all that, I end up with 2/3 x raised to the negative 1/3 minus 10/3 x raised to the positive 2/3. And then I just put it back in radical form because that's how it was given to me here. And so now all I need to do is, since I know that this is just a derivative of y with respect to x, then the derivative of y, or the differential of y in this case, is going to be f prime of x times dx. And so this will be the formula. So it's essentially whatever this is, put that in parentheses, multiply it times dx. So if we do the same thing here, notice that I could rewrite this function as just x plus 9x raised to the negative 1. So if I was to take the derivative of it, this would just be 1 plus, take the derivative here, this would be a minus 9x raised to the negative 2. So this will be 1 minus x raised to the negative 2. And this is equal to dy over dx. So therefore, dy is just going to be 1 minus 9x raised to the negative 2, all that times dx. And this would be the differential formula for this particular function. All right, so now we're going to do an example where we're using this differential formula here to estimate the change in our function, given we know the change in the x values. And so we're actually going to use this in an earlier example or analogy I was using. So we know that the diameter of a tree at a certain point in time was 20 inches. During the following year, so that means we waited a year, we see that the circumference had increased by 3 inches. So snapshot in time, we see diameter of tree was 20 inches. We waited a year later, and then instead of measuring the diameter again, we measured the circumference. And we see that the circumference of the tree had increased by 3 inches. Okay. So the first question that we have here is about how much did the tree's diameter increase? Okay. The second question is by how much did the tree's cross-sectional area change? Okay. So we have two different questions here. Notice that from this first question about how much did the tree's diameter increase, notice that what we know actually changed is the circumference, okay? But what we need to find out is the diameter. So what we need to be able to figure out is if D is equal to diameter and C is equal to circumference, let's try that again, then we need to be able to figure out somehow how can diameter be a function of circumference, okay? Similarly, if we look here for question number 2, we're asked to figure out how much the cross-sectional area changed. So if A is going to be the area, and of course C is going to be the circumference again, we're going to need to be able to figure out A as a function of circumference, okay? Because remember, circumference was the thing that actually changed. And so once we can find diameter as a function of circumference and A as a function of circumference, then of course the derivative of diameter with respect to circumference is just going to be D prime of C. And similarly here, the derivative of area with respect to circumference is going to be A prime of C. And so our goal here is to see how diameter and circumference are going to relate to each other, how area and circumference are going to relate to each other, so that we can come up with these formulas here. Because once we have this for question 2 and this for question 1, it is just a matter of multiplying both sides of this equation by DC, or here, DC as well, and we can just plug in what we need to, okay? All right, so this note that's here, since we're asked to find the increase in the tree's diameter and cross-sectional area, and we were only given information about the change in circumference, then, as I said before, we have to find diameter as a function of circumference and area as a function of circumference. So we're going to work on this first one here first, and then of course we'll work on the next one here second. So given the initial diameter of the tree was 20 inches, we also know that the change in circumference was 3 inches. All right, so I'm just listing a few things here. Even though we're not going to use this for now, I know that area of a circle is going to be pi r squared, and I know that the circumference of that same circle is going to be 2 pi r. Okay. Put it another way, the circumference is just a derivative of the area. Okay. Now, since we know that the diameter is going to be half of the radius, and notice that both of these functions here are in terms of the radius, then I'm going to express my diameter as diameter divided by 2. Okay, so that means my circumference, because remember, we need to express diameter in terms of circumference here. I know that my circumference is going to be expressed as 2 pi times diameter over 2, which is just going to be pi d. Okay, and some of you may have already known that that was a direct relationship, but I'm assuming that you may not have, so that's why I just derived. So because of that, of course, we could rearrange C is equal to pi d to solve for diameter, and so we see that diameter is just going to be circumference divided by pi. Okay, so this is diameter expressed in terms of circumference. So of course, if we take the derivative of the diameter with respect to circumference, of course, the pi is a constant, and the c here is acting just like an x would. So if we had a constant times x and we took the derivative of that, it would be just that constant. So similarly here, we know that the derivative of c divided by pi is just going to be 1 over pi. Okay? And here, I go ahead and take, say the derivative of diameter with respect to circumference is just going to be d prime of c, get it into the differential form. And then afterwards, I know that the derivative of diameter with respect to circumference is just going to be 1 over pi. So that's what I have here. So now I have a way of expressing the estimated change in diameter with respect to circumference. Okay. And so for this first question here, it says, by how much did the tree's diameter increase? Now that we know that circumference changes by 3 inches, we can just literally plug in, let 3 inches here equal d, or the differential of circumference. Okay. And I'm going to wait to the end to do that. I'm actually going to do the same kind of derivation we did for the first question for the second one, and then do them both at the same time. All right, so here, just want to remind you, we're going to hold this thought here that we know that the circumference changes by 3 inches. So I believe that's right. Let me remember here. Yeah, circumference. Yeah, so circumference increases by 3 inches. So we're just going to use this, and whatever this answer ends up being is going to be the answer for that. And we'll calculate that at the end. All right, so for question 2, remember we have to express area in terms of circumference now. So this is why I had the area of a circle formula. Of course, circumference is just still c equals 2 pi r. Radius is half of diameter. So we see here again that radius, our radius here, because remember we got to try to make area be expressed in terms of circumference. So I need to take this and try to somehow get some variation of a theme of this wrapped up into here. So I take my circumference and I rearrange everything to solve for the radius, which is just going to be circumference divided by 2 pi. And of course that's r, and that's the same r that's here. So I can replace that r with circumference divided by 2 pi. And so that's what you're seeing here. So once we do that, we see that area in terms of circumference is just going to be circumference squared divided by 4 pi. So that means area as a function of circumference is c squared divided by 4 pi. And if I take the derivative of this function, with 4 pi being a constant and c being the independent variable, then I just get 2c divided by 4 pi, which is just circumference divided by 2 pi. So now I know what a prime of c is going to be, or the derivative of area with respect to circumference. So we use that in our differential formula here by first recognizing that a prime of c is the derivative of a with respect to c, rewriting it in differential form. And then from there, letting a prime of c, which was c divided by 2 pi, replacing that. And so now we see that we have the estimated change in area with respect to circumference here. Okay. And again, for this situation, what we know is we know that this DC is going to be the change in circumference. That's going to be the 3 inches. And this C here is going to be the circumference that it was in the beginning. Okay. And we weren't given that, but what we were given was the diameter. And if you remember, circumference is just pi times diameter. the diameter that we were given was 20 inches. So that means that the corresponding circumference is just going to be 20 pi. And so this will be the calculation that we'll make at the end here. So now you see I've actually handled all of this. So we put everything together here. And for this first one, you see that how much did the tree's diameter increase when the circumference changed by 3 inches? It was just 3 divided by pi, which is roughly 0.9549 of an inch. And how much did the tree's cross-sectional area change? Well, we know again that the change in circumference was 3. So we just plug in 3 here. And remember, we said that the circumference when the diameter, the circumference when the diameter was 20 inches is just going to be 20 pi. And of course, that ends up being 30 inches there. And so, in short, when the circumference of our tree changed by 3 inches, the area changed by, and this should be square inches, by the way. Yep. The area changed by 30 square inches, and the actual diameter changed by close to an inch. All right, let's look at the next example. Next example, we're given that area is going to be pi r squared, where r is the radius, that is in centimeters. We want to estimate approximately how much does the area of a circle decrease when the radius decreases from 5 centimeters to 4.7 centimeters, okay? So here, let's say this particular circle has a radius of 5 centimeters. This one here has a radius of 4.7 centimeters. And what we want to know is how much does the area decrease? So what is going to be this area inside of here? And of course, since it's decreasing, we know that the result should be negative, okay? So when we do our whole derivation here, we should come up with negative numbers. Now, notice that we are looking at area in terms of radius because the change that we got was in the radius. So here what we need to do is figure out, well, what is going to be the derivative of area with respect to radius? Well, that's just going to be 2 pi r. And of course, we know that as a circumference, but we don't really care about that right now. And here, again, we could express this as dA over dr. So therefore, if we want to express this in differential form, it would look like this. And this is going to be approximately equal to 2 pi r times change in r, okay? Now the change in r is going to be, we end up at 4.7. We started off at 5. And of course, that's a difference of 0.3 centimeters, okay? And of course, that's in the negative direction since we went from larger to smaller. The radius that we started off with was 5. So the R that you see here and here, I'm going to just name it R1. That's going to be 5 centimeters, okay? And that is what belongs here. So now that we know that, the change in area is just going to be 2 pi times 5 times the change in r, which is going to be this negative 0.3. And of course, that's in centimeters. So if we work all that out, then this is going to be 10 pi, and I guess 10 times a negative 0.3. It's just going to be a negative 3 pi. And we're told here to use 3.14 for this problem. So this will be 3 times 3.14. And this is going to be a negative 9.42. And of course, this will be square centimeters. So we see that if our radius decreases by 0.3 of a centimeter, then our corresponding area decreases by 9.42 square centimeters. All right, so for our last example, I wanted to kind of change the examples a bit and do something that related to money and not so much STEM type stuff. So here we have a company, and they will sell N units of a particular product after spending X amount of thousands of dollars in advertising, as given by this function here. So they're basically, what they're doing is they're tracking, hey, if we spend so much on advertising, this translates to this many number of units actually being sold. Okay, and so they've tracked that, and of course this is valid for spending anywhere from $5,000 to $30,000. Okay. Now the first thing they want to do is figure out, they want to approximate what increase in sales will result by increasing the advertising budget from $10,000 to $11,000. Okay. So to put this into perspective, let's say they're spending, these advertisement dollars weekly. So let's say at a certain snapshot in time, they spent $10,000 in the current week. What they're trying to do is to see if we spend the extra $1,000 in the next week, how much is that going to increase the number of units that we're selling? Okay, so that's the basic idea. Now, of course, our delta N here is going to be the actual change in sales, okay, because that's what we're trying to do, approximately what increase in sales. So whatever it is, that 10,000 is fine, but we want to know if we spend that extra $1,000, how much bang for our buck are we going to get? So we're going to define delta N as the actual change in sales. We're going to say that the differential of N is going to be the estimated change of sales, which can be approximated by taking the derivative of, and this is a prime here, taking the derivative of this function times the change in the amount of money that we're going to spend. And of course, in this case, the difference is going to be a positive $1,000. Okay. And of course, we're going to be expressing everything in terms of X in thousands. So that's just going to be 1. So here we know that the actual change can be estimated by the differential. And we're just going to find the derivative of this and then plug in what's necessary. So here we see that the derivative of our function 60x minus x squared is just 60 minus 2x. We see that we started off at 10,000, so that's just going to be x equals to 10. And so n prime of 10 is going to be 40. The change in the amount of money that we spent in advertising is going to be $1,000. So since x is defined in thousands, it's just going to be 1. And so now we plug everything into our differential formula. The dx here is just 1. We already know this is 40. And so this means that 1,000 extra dollars that we spend in advertising is going to translate to 40 more units being sold. Okay, approximately. Okay, so now we want to do the same thing, but we want to do it at the $20,000 level. So let's say we're currently spending $20,000 in advertising per week. We want to increase that by $1,000. We want to see, all right, well, how much bang for our buck do we get by increasing it by 1,000? So we do the same kind of thing. We know that the actual change can be approximated by the differential, which is going to be the derivative of our units function times dx. In this case, we went from 20,000 to 21,000. So we have to evaluate the derivative at 20, which is going to give us 20 here. And this is going to be, and I guess to put that into perspective here, N is going to be the number of units sold per $1,000. Okay. So what we're saying here is this is 20 units sold per $1,000. That's what that number means. And of course, the change again is just 1,000. So that's just going to be 1. We plug that all into our differential here, and we see that it's just going to be a 20 unit increase. Okay. So what you're noticing here is that if we spend $10,000 initially and then go to $11,000, we're moving more units here than if we were to spend $20,000 and then decide to spend an extra $1,000. So what this is telling you here for part B is that our market is starting to get saturated a bit because for the amount of advertising that we're spending, if we increase the amount of money, let's say by 1,000, we're getting less extra units moved versus if we spend less. Okay. And again, you got to decide, what is your goal? Is your goal to get just as many as possible, or is your goal to say, well, hey, we got this much growth? Okay. And so this example here kind of shows you that. Going from $10,000 to $11,000, the change in sales is more sensitive than it is if we were spending $20,000 and just going to $21,000. So that's another way you can look at it. All right, so this ends this video on talking about differentials and their applications with linearization of a function. Take care.